Welcome to this webinar presented by the IET Anglian Coastal Local Network, which represents members in Norfolk and Suffolk. And welcome also to folks from other parts of the UK and indeed globally. I'm delighted to welcome you all. I'm Kevin Foster and I'm chairman of the Anglian Coastal IET Local Network, and I'll be your host for this evening. I'm delighted to introduce our speaker, Graham Murchie. Graham is a board trustee of the Bawdsey Radar Trust. He's a former chairman of the Radio Society of Great Britain and non-exec and former senior manager at BT Group. Now, 2020 was the 80th anniversary of the Battle of Britain. The COVID-19 pandemic prevented us from presenting last year. So today, Graham will provide a timely reminder of the early development of radar and how it was used successfully in operation in the Second World War. So Graham, over to you.
Thank you, Kevin, and good evening, everyone. I'm going to give a brief history of the scientists involved with the development of radar and Bawdsey's role in that. For those of you who don't know, Bawdsey is on the coast of East Anglia. The nearest town is Felixstowe, which is just across at the mouth of the River Deben from Bawdsey. What you can see on the slide at the moment is the concrete bunker that was the world's first radar transmitter, or the site of the world's first radar transmitter, and is now a Grade 2-star listed building. So let's go back in time to 1886. Heinrich Hertz, I'm sure everyone on this call will know that Hertz is the unit of frequency these days, but building on work he did by the Scottish scientist James Clerk Maxwell in 1886, Hertz proved that energy in the form of electromagnetic waves or radio waves could move through the air without wires and could be detected. Okay, a breakthrough moment, and if you like, the foundation stone for the development of radar. And if I really stretch my imagination, Hertz could be called the great grandfather of radar. But when asked about his development, he said, well, it's of no use whatsoever. We have these mysterious electromagnetic waves we can't see with the naked eye, but they are there. And asked about the application, nothing, I guess. So moving forward, 1904, Christian Holzmeier, another German scientist, as Hertz was, and he was an inventor and much more pragmatic. He was built on Hertz's work, and he could see potential commercial and practical uses for radio waves. He lived near the River Rhine, and he knew that during the foggy periods, ships on the Rhine quite often were crashing into each other. And he thought maybe we can use these radio waves to detect where the ships are. And he built what he called the telemobiloscope. And this was used to detect the ships. The radio waves distorted when they bounced off an object. So that potentially was the first operation of what we now may know as radar. But he got very mixed reviews, and the invention was not particularly a commercial success, although intriguingly, there was a newspaper article at the time about the telemobiloscope. And that said, and I quote, "Because above and underwater metal objects reflect waves, this invention might have significance for future warfare. Not radar as such, as Holzmeier's invention didn't measure distance, but it was another step towards radar as we know it today. And much more genuinely, we could probably call Holzmeier the grandfather of radar." So we can see that much of the early work that ultimately led to radar was carried out, ironically as it turns out, in Germany. So let's move forward to 1914. During the First World War, Britain had suffered 103 Zeppelin and bomber raids, which killed about 1,400 people and injured a further 3,400. This picture happens to be of Felixstowe on the East Coast, because most of the bombing was along the East Coast and into London, but little further inland because of the distance that planes could fly at that time. On the 13th of June 1917, 14 German Goethe twin-engine bombers released 72 bombs over London, killing 162 and injuring a further 432 people. The key thing was all the German planes returned to their base intact. So, Stanley Baldwin, we've moved forward again to the 1930s. Stanley Baldwin, former Prime Minister, and actually at the time effectively acting Prime Minister, as Ramsay MacDonald was suffering from ill health. He made this comment based on the experience of the First World War, that the bomber will always get through. The distance, the map hasn't changed, but the distance and the time between the coast of the continent, France and Belgium, and the UK, the time was much shorter. By the time we got to the 1930s, aircraft could fly higher, they could fly faster, and they could drop heavier bombs because they could carry a much greater payload. And as I say, the coast of the continent was very close. So how were we going to detect the incoming aircraft and not suffer as had happened in World War I? Well, the first attempt was building concrete ears, ellipses, parabolas, all sorts of geometric shapes with microphones at the focus. You can just about see that in the one on the left. These were great. They were huge. The one on the right was about 200 feet long, and some of them can still be seen there today. They're still there on the Kent coast. So the theory was they reflected the sound into the microphone, but the speed of planes, as I said, had increased, and therefore it was quite often that the planes were virtually overhead before they were detected. And also, if it was a windy day or the sea was rough, then the sea or the wind drowned out the sound of the aircraft. And the classic example was that the day the Air Ministry came down to observe how useful these were, what did they hear? They heard the milk float going along the road nearby and the milk bottles rattling in the crates. But they didn't really achieve much in the way of detecting aircraft in the right sort of time frame. Winston Churchill, still early to mid-30s, was obviously not Prime Minister at the time, but he did sit on a number of very influential parliamentary committees, and he was convinced with Hitler coming to power we were going to have another world war. So he said the flying peril is not a peril we can fly from. We cannot move London. We shall have to face this peril, whatever it may be, where we stand. So we've looked at the scientists who developed the theory and then potentially the practice of radio waves and how they might be used. We've seen the terrifying effects of aerial bombing in the First World War. And of course, for the very first time, the casualties weren't just occurring on or near the front line. So the reality of war was being experienced firsthand by civilians in the First World War. So we just had to find a way of detecting these aircraft because they would be over London much more quickly than they were during the First World War. So in November 1934, the Air Ministry set up the Tizard Committee, run by Henry Tizard. It was a small team of people and they were charged with strengthening and speeding up air defence plans. And they got to work. The secretary of the committee was AP, known as Jimmy Rowe. He's important because he became a key player in the development of radar and was actually based at Bordsey during part of the development activity. But he said, unless science could evolve some new method of aiding air defence, we were likely to lose the war if it started within the next 10 years. And as we all know, from 1934, the war started 5 years later. Now, one of the activities that the Tizard Committee had encountered was rumours about a death ray machine that the Germans had been looking at. And the Tizard Committee asked Robert Watson Watt, who was a physicist and a Scottish meteorologist who was using radio waves to plot thunderstorms in order to warn aircraft and pilots. They asked him to look at this wider problem, but in particular they said, what about this issue about a death ray? And the Air Ministry at the same time had offered a reward to anyone who could kill a sheep at 100 yards. So there was £1,000, a reasonable amount of money in those days, on offer to anyone who could develop a death ray weapon that could kill a sheep at 100 yards. I can absolutely assure you no sheep were harmed, and but the question was, could some sort of ray be used against a pilot? Robert Watson Watt asked his technical assistant, Arnold Skip Wilkins, to have a look at this. Skip Wilkins very quickly worked out that the power needed to bring down a pilot or kill a sheep at 100 yards would be, to put it mildly, enormous. In other words, it was beyond the generating capability of the UK at the time, so was a non-starter. So they advised the Tizard Committee that the death ray machine was not going to be viable. But Skip Wilkins remembered having read a paper written by a GPO engineer who was based at a shortwave radio receiving station. And this engineer had complained that when an aircraft flew near the receiving station, the radio waves were on occasions distorted. So Wilkins stood back and said, well, what are we trying to achieve? Are we trying to kill the pilots, or are we trying to detect where the aircraft are? So there was a faint glimmer of hope, and that was an idea that became the light bulb moment when operational radar effectively took its first breath. I've talked about the great-grandfather and the grandfather of radar. Robert Watson Watt is universally known as the father of radar. And Watson Watt himself called Skip Wilkins the mother of radar, because, to quote Watson Watt, no one did so much to give the embryonic war winner such a good start in life, hence the mother of radar. So as a result of this theoretical paper that Wilkins and Watson Watt put to the Air Ministry, they were asked to put forward a practical demonstration. And on the key date of the 26th of February 1935, a radio receiver with an oscilloscope was installed in the back of the van, as you can see in the picture. This is a pretty faithful painting of what happened. You can see two receive dipoles. If you look very carefully on the horizon towards the left-hand side, you can see some masts, and they're the masts of the BBC Daventry transmitter on around 49 meters. And the Hayford bomber was flown backwards and forwards between the transmitter and the receiver, and each time it travelled between the transmitter and the receiver, the trace on the oscilloscope wobbled up and down. And this was sufficient to convince the men from the Air Ministry there was something in this experiment that was worthwhile investing in. Now, for those of you that are interested, the receiver that was actually in the back of that van is, I'm told, now in the Science Museum if you want to go and look at it. So following on from the Daventry experiment, and with a budget of £12,300, which is about 850,000 in today's money, a team was set up at Orford Ness. This is on the east coast. It's a spit of land, a pretty bare spit of land that had been used for all sorts of testing since the First World War. The team was set up, and within a few months they could detect aircraft up to 60 miles away, and they had devised a method of measuring height and direction as well as distance. Slight aside, this slide's headed Bordsey Boffins. There is allegedly a story that the word boffin first was used either at Orford Ness or very soon after at Bordsey, but it's only allegedly, but that seems to be where the word boffin came from. So Watson Watt was very keen to progress and keep these things moving, and he adopted the cult of the imperfect. He told his scientists and developers, give them the third best to go on with. The second best comes too late, and the best never comes. The Germans adopted, as ever, the Teutonic approach of going for the best. And when we did capture elements of German radar, they were extremely well built. But if you look at pictures of British radar, very early operational pictures, then you can see there were components spread all over benches, even though they were pseudo-operational. But this approach of give them the third best worked remarkably well. So the team pretty rapidly outgrew Orford Ness, and so the Titog committee allocated some £4 million towards building the first radar stations. In 1936, the team moved from Orford Ness to Bordsey Manor, and with its towers, its landscape gardens, swimming pool, tennis courts, it must have been absolute bliss to the people that had previously been on Orford Ness. They still have privacy and isolation. Bordsey Manor is in the middle of nowhere. I could almost argue it's on the edge of the middle of nowhere. You can see it's right on the coast. And even today, driving from the main road or Woodbridge, which is the nearest main town by land, Felixstowe may be close, but it's across the River Deben. Even driving to Bordsey today, it's a very windy road, and frankly, it is full of agricultural vehicles a significant proportion of the time. Sir Cuthbert Quilter had been building the manor since the 1890s. He sold it to the Air Ministry in 1936 for £24,000, about £1.5 million in today's money. Interesting, Cuthbert Quilter was a stockbroker, and depending on how much money he made each year, he would build different elements of the manor. And those that understand architecture tell me that there are at least 7 different architectural approaches to this building. So different towers built different years, etc., etc. Quilter was also the owner of one of the very early private telephone companies, and Bordsey Manor boasted the telephone number Woodbridge 1. So having developed the system such that they could detect aircraft at many tens of miles, then the first radar stations, as I said, the money was allocated by the Air Ministry, and the first radar stations were constructed east and south coast of Britain initially. Each of the early stations had 4 transmitter towers, each 360 feet high, made of lattice steel. The receiver towers were wooden and 240 feet high. There were 4 of those. So the very first operational station was built at Bordsey. The next 4 stations were built, 2 in Essex at Bromley and Canewdon, and 2 in Kent at Dunkirk and Dover. But it's all very well being able to detect the aircraft at Bordsey or any of the other stations, but what do you do with that information? And it was absolutely essential that there should be a command and control air defense system. And that was developed, leading to much better communications. So the pilots and aircrew needed the vital early warning to know where to be. So from the radar stations, there were telephone lines to Bentley Priory, where Fighter Command was headquartered, and then out from Fighter Command to the fighter stations through various steps. But equally important was the observer corps. Radar was great for looking out to sea, but it wasn't good at tracking aircraft when they were in land at this stage. So the observer corps were used and linked into the system called the Dowding system. They were linked in as part of the overall command and control system. Now, when we give this talk normally, there are quite a few people who don't necessarily fully understand the principles of radar. So I'm sure everyone on this IET call does so, but let me just run this 60-second video just to position for people how radar was used in the Battle of Britain rather than how it operates now.
The principle is wonderfully simple. Imagine dropping a stone into a pond and watching the ripples spread outwards. When these hit an object on the pond's surface, the ripples bounce back towards the starting point. Like the ripples in the pond, pulses of radio waves are transmitted from an aerial, travelling at the speed of light. These bounce off a plane and can be picked up by a receiver. The time delay between the pulse leaving and coming back helps to identify the range. By measuring the slight time delay noted between 2 receiver aerials, you can also work out the aircraft's bearing. Watson Watts and his research team quickly improved the range and accuracy of their radar experiments and proved that approaching aircraft could be identified from many miles away.
Okay, so that just explains the basic principles of radar. Another slight aside, the term radar didn't come into use until 1942 when the Americans joined the Allies. The activity was initially known as radio direction finding, partly to try and keep secret what was the whole activity of radar was about. Radar direction finding was used in the First World War to detect enemy transmitters, and so RDF was used to describe what was going on. And intriguingly, we do know that the German maps of 1940 had got all the radar stations around the south and the east coast marked as RDF stations and no more than that. So radio detection and ranging, radar as a term, only came into use in 1942. Now, it's all very well being able to detect, but how do you interpret and determine exactly what you're seeing at the receiving stations? As early as 1937, Robert Watson Watt had proposed that women should be radar operators. He said, I quote, "Their alertness, keenness of perception, delicacy of touch, and immeasurably above all else, their conscientiousness is to a degree unobtainable in the men. There you are. So as a result of Watt's support and the great work the women did, it was predominantly the Women's Auxiliary Air Force, WAAFs, who operated the radar systems throughout the war. They were called special duty clerks, another vague term to keep it secret. And by 1943, about 7,500 of them had been trained, the vast majority at Bawdsey. I didn't say that when war broke out on the 3rd of September 1939, the scientists and the developers were moved out of Bawdsey Manor immediately. They initially went up to Scotland and then moved to Dorset and then to Malvern. But they were moved out because Bawdsey was deemed too dangerous, either whether it was attacked by aircraft or whether raiding parties came, so they were moved well away. But operationally, it remained the key station, and it was used to experiment with a lot of new systems as they were developed. But the training took place there, as I've said. But the WAAFs had it imbued in them that this was secret. They were not to tell anyone. And the classic story is that a WAAF who was on duty in one of the Dover radar stations was awarded the military medal. And when she went to Buckingham Palace to collect her medal from the king said to her, "And what do you do?" And she replied, "I operate a telephone, Your Majesty." She did not tell him she worked on radar. It was kept secret as far as she was concerned from even the king. So what did they actually see? The trace they saw was, as you can see at the top of this, so the distance was shown in miles. You could see it was fairly normal to be able to detect well over 100 miles. And the WAAFs not only had to look at the distance that the aircraft were, but they very quickly learned how to detect from the dip in the trace whether there was one aircraft, 5 aircraft, or up to 200 aircraft. Because we could see over 100 miles, we were able to detect the bomber formations developing over Belgium or France before they started flying towards the UK. So this interpretation of how many, at what distance, at what height, and at what bearing was all absolutely vital information, because at the time the Luftwaffe outnumbered the RAF by about 4 to 1. So it was the use of radar that enabled us to get our Hurricanes and Spitfires in the right place at the right time to enable us to attack the incoming bombers. In fact, it was pretty key to get the Spitfires and the Hurricanes above the incoming force. So it was key that we were able to do that. Now, I mentioned that the Luftwaffe outnumbered us 4 to 1, and the German pilots were told time after time after time, the RAF have got far fewer planes than us. But every time they approached the coast of the UK, all they encountered was Spitfires and Hurricanes. So the German pilots began to disbelieve all the information they were told about the RAF being far smaller. They just didn't believe the information they were given by their senior officers. So it became, it was critical. So in the Battle of Britain, it gave us a decisive win. It delivered a massive blow to Hitler's invasion plans. Hitler planned to invade Britain in the autumn of 1940, but he only knew he could do it if the skies over Britain were under German control. They never were, because of the few controlled by radar. So the threat of invasion was off. And again, to quote Churchill, all the ascendancy of the Hurricanes and Spitfires would have been fruitless but for this system which had been devised and built before the war. Now, we have all heard about the few, and we know about the Battle of Britain. The most authoritative book that's been written on the Battle of Britain was probably written by a guy called Stephen Bungay. Stephen Bungay went into great detail. He looked at the Battle of Britain day by day. Each individual day was analysed between the beginning of July, end of September, and he looked at which pilots from which airfields, which wings took off, equally the same for the Germans. Intriguingly, he also looked at the number of aircraft shot down, number of claimed aircraft shot down by each side, and obviously with hindsight was able to compare that with the actual number that were recorded as being damaged or destroyed, and lo and behold, the numbers didn't match up that well. But towards the end of his book, he put forward, he recognises a few, but he put forward perhaps what could be called the alternative few. I'm just going to very quickly go through 10 names. Some of those names you will recognise, some you probably won't. You may well not know the first one, Major General E.B. Ashmore. He was in charge of London's air defences in World War I, and in 1917 he laid down the principles of the Dowding system. He created the Observer Corps, the plotting and recording system, and the telephone network. And when Dowding took over Fighter Command in 1936, he resurrected Ashmore's system, and it became absolutely key to winning the Battle of Britain. I've already mentioned Sir Henry Tizard. He led the scientific approach in dealing with the threat from the air. Robert Watson Watt, I won't expand on his contribution, absolutely key, and just to remind you that he's still known as the father of radar. The next three can almost be considered together. Sidney Cam designed the Hurricane, Reginald Mitchell designed the Spitfire, and Ernest Hives led the team at Rolls-Royce which produced the Merlin engine. So the Hurricane, the Spitfire, both powered by the Merlin, were absolutely key to the Battle of Britain. You may not have heard of the next one, Ralph Sawley. He may perhaps be the least known of these few, but he was instrumental in convincing the Air Ministry that Hurricanes and Spitfires should be armed with 8 rather than 4 guns each. And this decision turned out to be absolutely crucial in the Battle of Britain. Sir Hugh Dowding, Air Chief Marshal Dowding, brought all the key activities together. And what is still known as the Dowding system laid the foundations for victory in 1940 and beyond. We must mention Winston Churchill. He didn't get directly involved, but he could see the big picture, and when necessary he intervened decisively on critical issues. And some of the stories will tell you that Dowding sometimes wished Churchill wasn't quite so interested in being at Bentley Priory, but there we are. Last but by no means least, Air Vice Marshal Keith Park. He was at the sharp end, leading 11 Group, which covered the southeast of England, stretching from Lowestoft to Southampton, including, of course, London. And he took the really instantaneous decisions which resulted in ultimate success in the Battle of Britain. But once the Battle of Britain was over and the Blitz started, the German aircraft started flying over at night. The original chain home transmitters with their huge towers weighed 6 tons each. They could get an aircraft to within a few miles of the incoming bombers, but only within a few miles, which is great on a day like we've had today, which is very sunny. And those of you who have seen the Battle of Britain film will know that a fair number of days during the Battle of Britain were a bit like today, hot and sunny. But if it was cloudy or if it was at night, then the Hurricanes and Spitfires couldn't necessarily find the incoming aircraft. So how do you get close to the bombers at night? So further developments of radar, air-to-air radar had to be developed. Huge size and weight challenge, as I say, the original transmitters were 6 tons. This activity was led by a guy by the name of Taffy Bowen, and he gave his team in 1937 a target of 200 pounds weight for the equipment to go into the aircraft. The original chain home experiments were carried out at 50 meters, around 7 megahertz. The 6 or 7 megahertz, the ultimate chain home transmitters in 1939, 1940 operated around 24 meters, around 13 megahertz. But for the aircraft-borne radar, they reduced that by a factor to around 200 megahertz. The original pulse width was around 20 microseconds. By the time the war started, it was about 4 or 5 microseconds for the chain home systems. The onboard aircraft reduced that to 1 microsecond, and therefore using triodes that had developed, they could produce about a kilowatt of pulse power by June 1939. But not only air-to-air, but air-to-surface vessel radar was important. And the aircraft had forward-looking and side-looking antennas on some of them. Side-looking antennas gave a much broader beam width, so that you could detect roughly where a ship was. And of course, you all know what happened with the Atlantic convoys and the fact that the U-boats attacked them. The weakness of the U-boat, of course, was that it had to surface at night to recharge its batteries. So by 1940, aircraft were able to detect large ships at about 60 miles, and again in 1940, the first submarines were detected. But the real step function came with the use of the magnetron. Magnetrons have been around for a while, but in 1940, Randall and Boot at the University of Birmingham developed the cavity magnetron that produced multi-kilowatt pulses at a frequency of 3 gigahertz. By the time we're into the gigahertz, then you can get huge gain from much more directional antennas, and this was absolutely key to the ongoing activity with radar, particularly airborne radar. And of course, the cavity magnetron is still in everyday use. I would guess that probably 95% of people on this call have got a magnetron in their house, and over 50% of you have probably used it today, because of course it provides the power for your microwave oven. Slight aside again, but key to the magnetron issue, Churchill decided in September 1940 to send Tizard across to the USA to try and encourage the Americans to join us even more than the support they were giving us already. And the team, the mission, took across a whole host of items. They took across a working magnetron, which interestingly an American historian described as the most valuable cargo ever brought to our shores. But they also took the proximity fuse, the VT fuse, the details of Frank Whittle's jet engine, the memorandum describing the feasibility of an atomic bomb. And those may be considered the most significant, but they were also designed for rocket superchargers, gyroscopic gun sights, submarine detection devices, self-healing fuel tanks, and plastic explosives. Huge number of things. The reason for mentioning this is that during the course of the war, the Americans manufactured 1 million magnetrons or thereabouts, many of which were shipped back to the UK for use by the British. So just before I finish, what happened to Bordsey post-war? 1955, during the Cold War, RAF Bordsey was manned 30 minutes before dawn until 30 minutes after dusk. Nobody has been able to explain to me why the USSR would only attack us during daylight hours, but there we are. 1963, all the receiver towers were demolished, leaving just 2 transmitter towers. And also in 63, Bordsey became a Bloodhound missile control site. 1979, Bloodhound Mark IIs were located at Bordsey. Those of you who live locally and are sailors will have seen the Bloodhounds from the sea. Those of you coming in on the ferries into Felixstowe or Harwich would have seen the Bloodhounds, and from certain inland sites you could see them as well. 1990, all the missiles were withdrawn. 91, RAF Bordsey officially closed. 2000, the last tower came down. 2004 was a key date. That was when the BBC ran the restoration programme, which took either 8 or 10, I can't remember exactly which, buildings that were considered at risk by Historic England, or whatever they were called in 2004. And the Bordsey transmitter block was one of those at-risk buildings. We didn't win the restoration programme, but the Bordsey Radar Group was established to look after the transmitter block, and that group developed the activity such that in 2017 the transmitter block was refurbished with a grant of £1.4 million from the National Lottery, which enabled us to turn the block into the museum that it now is. So I've explained that what happened with Bordsey. Bordsey Radar is now a registered charity, and we do rely on visitors for our income. Obviously, as Kevin briefly mentioned at the beginning, 2020 was not our best year, but not anybody's best year. And so we had virtually no visitors. So what we did, we very rapidly changed our physical shop that's in the museum to an online shop. And we have quite a few radar related, unique to Bordsey Radar items. So please go to bordseyradar.org.uk to look at the shop. You can also, if you wish, make donations to help keep us going and help keep the story going. You can register for our newsletter. We have reopened. We reopened as a museum a week ago today. So we open on Thursdays and Sundays. You have to pre-book at the moment. Again, go to bordseyradar.org.uk. But we are getting quite a reasonable number of visitors, which is absolutely great. But finally, please come and see us and visit the museum. We'd be delighted to see you. Okay, so I'll willingly take any questions. I'm sorry that was a mad dash through, but please ask questions.
Graham, that's absolutely fascinating presentation.
A couple of questions from Dave Sinclair, which are related. How did the radar of 1936 do direction and altitude detection? What frequency, pulse width, etc. did they use? And did they have to manually calculate the bearing from the time difference of received pulses at the 4 towers, or was there some sort of computer?
Okay, let me see if I can remember. You might have to remind me if I miss bits. So height and bearing. Height relied on the aerials on at different heights, and the time difference, the minimal time difference between the different heights enabled the height to be calculated. I think the video showed the direction was between two different aerials side by side. That's why there were 4 towers. The aerials were physically separated horizontally, if you like, and that enabled the bearing to be detected. And yes, there was what we would perhaps call a computer now, which was based on post office technology, uniselector technology, etc. It was pretty crude, and in fact, the museum had an activity to visit the BT archives in London to go and look in more detail and work out more detail of what was called the fruit machine that enabled some of these calculations to be carried out. I think another part of the question was about pulse width, and I think I covered that perhaps in a later slide or towards the end. Early pulse width was around 20 microseconds and reduced as time progressed, and certainly down to 1 microsecond pulses in later versions of radar. Have I missed anything, George?
Frequencies.
Frequencies, again, I think I might have touched on that. Very early frequency was 50 meters, based on the fact that the wingspan of a bomber averaged around 25 meters, which was a half wavelength, but 50 meters didn't work particularly well. So eventually the chain home system ended up at around 24 meters, around 13 megahertz.
Okay, really a comment from Philip Benstead, where he notes that the UK may not have been the first to develop radar, noting in 1933, Rudolf Kuhnholt demonstrated radar that became Freya. It went into production in 1938, and in 1933, the Russian army developed a continuous wave system, Rus-1, that was first to go into production with a batch of 6. So I don't know if you want to position that in relation to...
I can comment on that, and yes, I'm not sure of the exact dates. If you want the exact dates, as I'm sure Phil Judkins, I believe, is on this call, so he would be the man that could comment if I get anything dramatically wrong. And thank you, Phil, for your input to the presentation. But coming back to the point, yes, the Germans did develop radar. Thanks again to Phil, who I've just mentioned. Borzi Radar do a completely different talk that lasts yet another 40 minutes about how the Germans got the story of our radar so totally wrong. One of the reasons was their development of radar was based more on what we understand as radar today, with the spinning aerials that are constantly going round. We didn't have that. The Germans did have that, and the Germans assumed that if we were going to develop radar, we would use the same system. We didn't. We did if you like, a floodlighting using the towers. But there was also a lot of politics and personalities on the German side, with Goering and Hitler. Goering, for example, had been a First World War fighter ace, and as far as he was concerned, he didn't want this newfangled idea of radar. As far as he was concerned, you just let the fighters get on with it. They didn't need to be told where to go. He wasn't told where to go in the First World War. And the other thing was, Hitler was not interested in defense. Hitler was interested in attack. And all he wanted to know was how many aircraft have the French got, how many aircraft have the British got. So there was no real political support for radar inside Germany. Yes, they developed it, but the first operational systems that were viable were was the one at Borzi, and then the chain home system around the coast. But that again was combined with the Dowding system. The Germans could detect our aircraft using Freya and other systems, but they didn't link it to their fighters. So that's the key difference. And as I say, there's a whole different story all about that. Hopefully that's sufficient with that one, George.
Okay. More of a comment from Philip Benstead, but maybe you could comment on the comment, Graham. Skip Wilkins made a very unique contribution to radar. He developed a formula that converted the direct slant propagation delay time from the target to a position in map grid terms. We still use his slant range formula in primary radar data processing. Is that something you want to comment on?
I can't comment in great detail. What I do know is that the work that Wilkins did was absolutely brilliant, and a lot of what was developed by Wilkins and the team is in use, maybe in a modified form today, but I can't comment on in detail on the specific issue.
Okay, a question from Keith. Are there any remaining examples of the early chain home transmitters in existence?
We're asked this on a fairly regular basis, and we believe the answer is no. If there is anyone on this call that has got a chain home transmitter, then we will be delighted to hear from you. But our understanding is there are odd bits, but no complete transmitters. Some sites have, as I say, odd bits, but nothing complete, sadly.
Okay, from David Peck, who thanks you for a very enjoyable talk, and he has 3 questions. And can you describe examples of the difference in the trace as a function of the RAID's number of aircraft and aircraft type?
The trace, I'm not sure that the WAFs could detect the aircraft type, but the trace, the depth and the width of the trace, they were able to interpret reasonably well. And again, it varied by distance. And this was very much a matter of experience, but they could, by looking at the width and the depth of the trace, they could determine to a degree how many aircraft were in any formation.
David asks a second question. What, when and how did the Germans know about our radar capability?
Well, they didn't know a great deal, certainly at the beginning. In August 39, they sent an airship up and down the East Coast, trying to work out what all these masts were that had appeared at Bordsey and the other sites. And this is again part of our other presentation, but having spent a significant period of time going up and down the coast, all they could really detect was a 50 hertz signal. And that 50 hertz signal, they assumed wrongly, was just our development not being very good, or the national grid leaking interference. So all they could hear was a 50 cycle signal, which they interpreted as nothing directly to do with radar. In fact, the 50 hertz mains frequency was used to synchronize the different transmitters at the different sites. When they really learned about the capabilities of our radar was certainly after the Battle of Britain, and they did attempt to attack radar stations on a number of occasions. Bordsey was attacked 2 or 3 times, and I think 3 or 4 people were killed on the Bordsey site. They didn't put the transmitters out of action. They did attack the Dover and the Isle of Wight stations rather more, but very rarely were they put out of action. And on the one occasion where they were put out of action, then the we had mobile systems that could fill the gap. Not so well, but as far as the Germans were concerned, nothing ever happened in terms of loss of radar signal when they bombed our sites. But it's intriguing how the Germans got the story so entirely wrong.
Did the Germans jam or use chaff against our radar, and was it successful? So that's David Peck's final.
They did attempt to do some jamming. Certainly there was an element of jamming when the battleships, I can't remember, was it the Scharnhorst and the Graf Spee or wherever, tried to escape. There was an element of jamming around that time of the radar that was looking lower at sea level, but we were able still to detect the aircraft that were flying as a protection over the battleship. So yes, they did attempt it, but we could move frequency and did move frequency from time to time around 24 meters.
Okay, a question from Mike Edkins, who noted that his father served on AA anti-aircraft radar. Do you know the format of that radar?
Well, the anti-aircraft radar was developed as part of the Bordsea development. I don't know much detail. There were a whole series of teams, but I can't remember who led the anti-aircraft radar team. But the initial work was carried out at Bordsea, and more than that, I can't tell you off the top of my head. I can certainly find out more information if the questioner wants to ask me.
From Paul Darlow, was any effective jamming achieved by Germany during World War II?
Not greatly effective. Yes, there was jamming, but generally speaking, the radar systems detecting aircraft, incoming aircraft, were not dramatically jammed. The Germans did jam signals where we were using radio beams to guide our aircraft, as we jammed theirs, of course, when they were using radio to tell their bombers when to drop the bombs and guide them along the right glide path, etc.
Okay, a question from Simon Watts. Two transmitter towers on Chain Home supported one transmitter array tuned to a certain frequency. What was the tuning bandwidth of a single array? And how was the frequency of operation chosen, and how often did they have to change frequency?
Good evening, Simon, and thank you for that. I cannot answer that question, to be straight with you on that. Yes, the dipoles or the antennas were strung between the masts. I don't know how often they changed frequency. I think that varied very much from depended on the particular circumstances, but I'm sure your friend Mr. Judkins, Dr. Judkins, can answer that question far better than I can. I'm sorry I'm not able to answer it off the top of my head, but I will take it away and I will tell you in due course.
A question from Andy Flack, and who is asking if he remembers correctly that the remaining tower at Great Baddow in Essex is a rebuilt tower from Bordsea.
No, the tower at Great Baddow in Essex is the tower that was moved, I think, from Canewdon, not from Bordsea.
Question from Mark. How did radar cope with V1 and V2 rockets?
Oh, well, it certainly was used to detect V1 and V2. It had been developed quite considerably by the time that V1 and V2 were developed. And it was used to try and not only detect incoming V1s, but also the they used it to try and identify where the V1s had been launched from. But of course, the Germans, I think if I remember correctly, with V1s have mobile launchers, but I don't think they did with V2s. And as I understand it, one V1 landed on the beach at Bordsea, and a V2 blew up somewhere over the sea, not far from Bordsea. But it was used in subsequent developments to detect incoming V1s and to try and backtrack to the launch site.
A question which might be a more intriguing one from Jay Simner, who notes that his father-in-law worked on radar for the Admiralty during the Second World War, and that he featured in a black and white film of their activities. And there was an actor playing his father who went up the tree with a balloon. Now, is there a chance that you know the name of this film?
I don't, I'm afraid. Again, Phil Judkins might, because he knows everything. No, I don't recognise. We do have one or two black and white films, but many of them were training films because, of course, in those days, the people on site at Bordsea were not allowed to have cameras, although we did have an intriguing visit by a 99-year-old lady about a year or just before lockdown, who brought pictures of WAFs at Bordsea. And we said, how come you've got these pictures? Oh, they didn't know I had my camera, dear. But no, seriously, the film, I don't know that one, but there are a number. We've got a classic John Snagg film, the BBC newsreader, who was obviously let into the secret of radar because he did the training film for the WAFs, explaining how to operate the tracers on the oscilloscope.
Graham, does the museum know the names of the scientists and engineers who worked at Bordsea? Some of whom he believes, Ian B believes, such as Hanbury Brown, went on to do great things in radio astronomy.
Oh yes, there were there were Sir Bernard Lovell, Martin Ryle, who are well known from astronomy perspective, were very involved with the development of radar. Yes, we do, as I understand it, have a list of the vast majority of people who were based at Bordsea. I won't say we know everybody, but I'm pretty certain we know all the people who were involved on the development side, the scientists, etc., at the early stages. In fact, there is a classic of the civil service at the time. Robert Watson Watt, Skip Wilkins, Taffy Bowen, and several others were all listed in the civil service list as being at Bordsea Manor. That was their headquarters, including, I think, the telephone number and how much they were paid per year in the civil service list. And the civil service list was issued to all embassies, including the German embassy. So that's another classic example of how to keep something secret. But again, the Germans didn't match the names to some of the papers that those people had published prior to them becoming involved in radar.
I have some. Do you know the names of the people in the boffins photograph you showed?
I don't off the top of my head know. Whether we have that record on the back of the photograph, I honestly don't know.
Okay, and do you know of a person called Helmer Dahl, who was Norwegian, who worked on radar in the UK on 3 gigahertz in 1940?
The name does ring a bell, a very vague bell with me, I think. But I can't place, I have read many books about radar, and I'm pretty sure it was in one of those books that I came across his name, but I can't place exactly what he did.
A question about chain home. Why was the system called chain home?
It was a chain of radar stations protecting the home of England, if you like. That's my understanding of why it was called chain home.
Okay. Did the recovered German radar from Bruneval raid have an effect on radar design in the UK?
I believe it had some effects, because we did look at that in great detail, and that's where we found this wonderfully engineered technology. So yes, we stripped that apart and took it apart in great detail. Interestingly, one of the main effects the Bruneval raid had, it moved the scientists from Worth Matravers in Dorset to Malvern. That's what precipitated the move, because we decided that if we can raid Bruneval, then the Germans could raid Worth Matravers. So we moved the development team way inland.
Right. A question from Richard, which I think you answered in part. Are we able to visit the Bodsey bunker?
The Bodsey bunker is open Thursdays and Sundays, but you have to book in advance. But yes, we'd be delighted to see any of you. In fact, we'd be delighted to see all of you there.
Okay. How are we doing on time? Probably another couple, if that's okay with you, Graham.
Sure.
A note from Alan Hartley Smith, who suggests that on working transmitters, suggests contact the Neatishead Museum, RAF ADRM. So I guess that's an acronym for something which I don't know.
No, we're fully in touch with Neatishead, and yes, we know Neatishead well. So thank you for that.
And you've mentioned Worth Matravers and Dorset Coast and how it linked. But I've got a question from Phil Rudd. With which radar system was swept gain first applied, and what were the early techniques used?
Pass, I'm afraid. I can't answer that one.
Okay. Can we try one final one? I've heard of chain home low. This is Jim Amos. How did this differ to the chain home system in frequency, etc.?
Chain home low was developed to because what the Germans discovered was that the existing chain home system wasn't able to detect the aircraft below. Oh, I'm trying to remember the exact the height, and I can't remember the exact height below which the chain home system operated. I'm rapidly trying to rack my brains, but the chain home low, I've got a brief note about that somewhere. I'm just seeing if it lists the frequency. Yes, they moved to about 200 megahertz as part of the air interception work, and so I think what they did, they installed a 200 megahertz system on the one of the platforms on the transmitter tower, and were able to detect an aircraft flying down to around 500, yes, around 500 feet at about 25 miles away as a result of moving to chain home low. And then in due course, they actually went to chain home extra low, but and that went down to around 50 feet. I'm not sure what that, I think, was when they moved to UHF rather than VHF, but I can't give you the exact frequencies. So there was chain home, then chain home low, then chain home extra low, and we could cover down to around 50 feet with extra low.
Well, thank you very much for answering so many questions, Graham. There are a few left, but I think we can't go on all night. I'd like to hand us back to Kevin Foster, our chairman.
Well, thank you very much, George and Graham. Thank you so much for an excellent presentation and for taking so many detailed questions. As a young boy growing up in Suffolk, I was always fascinated to talk to my father and my grandfather about, what went on at Orford Ness and what went on at Bordsey. And I think you've managed to fill several of the gaps in my knowledge. So thank you very, very much for all the work that you've put in for the presentation and for taking the questions. And you brought up the old magnetron, and that's where I started my career in sort of late 70s, working for English Electric Valve, and one of my placements as a student was in the magnetron division, making magnetrons. So that was very, very interesting. So thank you for all your work there. And my also thanks, George, for collecting the questions and asking the questions. Looking at this slide, I really want to draw your attention to our future Anglian Coastal IET local network webinars. We've got a couple coming up in July. The first one is by Gavin Young from Vodafone on quality attenuation and its impact on understanding broadband performance. I think we've all been sort of very, very aware of the importance of broadband, especially the last 18 months or so when we've had to work from home. And it's all very well having a fast connection, but you need good customer experience as well in that broadband connection. So Gavin will talk us through some technology that's been developed to measure quality attenuation. The second webinar will be on the 7th of July, and that will be about the World War II mosquito. The exact title of the presentation is subject to change, but Tim Stevens will give that one on the 7th of July. So those two, Gavin Young from Vodafone on the 1st of July and Tim Stevens on the 7th of July. They're both, please look out for those, and details of how to register with those and register for those are on our IET Communities website. So before we close, I'd just like to draw your attention to Foothold, which is a support for engineers needing support in the difficult times. Over the last 18 months or so, it's been particularly difficult for a number of us working in the engineering community. If you need any support, Foothold is there for you. So I'd just like to mention that before we finish. So finally, on behalf of the IET Anglian Coastal Local Network, thank you all for joining tonight. And thank you again to Graham for an excellent presentation and to the team who put on tonight's webinar. Now, that concludes the webinar, and you may disconnect now. Thank you.